Welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 5th, 2025. Alright, so today we're looking at an interesting ICLR conference paper published just over 3 months ago, back in January. Latent Bayesian Optimization via Autoregressive Normalizing Flows. This paper tackles a key issue in latent Bayesian optimization, or LBO, where generative models like VAEs often struggle with a, quote, value discrepancy problem due to imperfect reconstructions. They propose using normalizing flows, NFs, instead. Okay, and this first figure really highlights that value discrepancy problem we just talked about. It shows histograms of objective function values for some top data points before and after reconstruction using a VAE-like model. You can clearly see the shift. The orange bars representing the values after reconstruction are much lower than the original blue ones. This visually confirms how reconstruction errors can really degrade the values, which is exactly what NFBO aims to fix. Okay, so this next figure really contrasts the old way with the new approach. Part A illustrates that standard LBO reconstruction gap. Encoding X, then decoding gives X hat, which isn't always the same as the original X, leading to that value mismatch we saw. But Part B shows how NFBO uses these invertible flows, mapping X to Z, and perfectly back again using the inverse. This guarantees the latent Z always corresponds to the original value Y. Alright, building on that idea of invertibility, this figure shows the actual pipeline for their proposed SeqFlow model, designed specifically for discrete sequence data. You see the input X, like tokens in a sequence, first gets embedded into a continuous space V. Then, the top pathway shows these autoregressive transformations mapping V step by step into the final latent Z. Crucially, the bottom pathway shows the exact inverse transformations, guaranteeing a perfect reconstruction back to the original X. Okay, so this figure puts it all together, showing the complete normalizing flow Bayesian optimization, or NFBO, framework. We see the SeqFlow model mapping the discrete input X to the latent Z, just like we discussed. Then, the Bayesian optimization itself happens over this latent space Z, training a surrogate model. And importantly, they introduce this token-level adaptive candidate sampling, or TA-SACS, which adaptively perturbs latent tokens based on their importance to generate better candidates for the acquisition function. Moving to the results, this figure shows how NFBO performs on actual molecule generation tasks from the guacamole benchmarks. We see plots comparing their method, the blue line labeled hours, against several existing LBO baselines, tracking the best score found versus the number of oracle calls. Across different tasks and budget settings, NFBO consistently finds better solutions faster than the others. This really demonstrates the practical advantage of eliminating that value discrepancy and using TACs. Okay, and this table digs deeper into the performance, specifically on the PMO benchmarks, which cover 23 different tasks. It compares NFBO, using the selfies representation, against a whole suite of methods, including other Bayesian optimization approaches, reinforcement learning, genetic algorithms, and hill climbing. Well, across 6 evaluation metrics like Top 1 Score and AUC, NFBO ranks number 1 in 5 of them. This really solidifies the strong performance we saw earlier on guacamole. So wrapping things up, the key takeaway here is how NFBO effectively tackles that value discrepancy problem using invertible normalizing flows, specifically with SeqFlow for sequences. Combined with the clever tax sampling strategy, it leads to really impressive, state-of-the-art performance in optimizing complex structured data like molecules. Alright, that's all for this AI Research Roundup. Thanks for tuning in, and see you next time.